Good day, grade 12s. In this video, I'll be revising the topic on assets and bases. So I'll look at some few previous exam questions on assets and bases. Maybe I'll do 2 or 3 of those questions. If you remember, during the trial examination, you were given a question that looks like this. So question 7 on your paper 2 September exam was saying, consider the ionization of oxalic acid, which is C2H2O4, represented by the following balanced equation. So here is a balanced equation that they gave you. So they said now the concentration of each of the substances found in a 0.1 mole per cubic decimeter solution of H2C2O4 at equilibrium is given in the table below. So you have now these 3 substances, H2C2O4 with this concentration of 0.046 mole per cubic decimeter. HC2O4 is 0.05 mole per dm cubed. H2O4 plus is 0.054 mole per dm cubed. So these are the concentration of these substances. Now let's look at the first question. 7.1.1 says define an acid according to Lorentz-Bronsted theory. So that is your 2 mark. The definition says an acid is a proton donor. So that is your 2 marks. 7.1.2, write down the formula of a base in the above reaction other than H2O. Write down the formula of a base other than H2O. So if you look at this reaction, now if you look at the left, H2C2O4 is an acid because it donates a proton to H2O. So it's an acid. Then this is the conjugate base, which is HC2O4 minus. Then the water that received a proton there was a base. And then this is each conjugate acid on the other side, H3O plus. So they said we need to write now another base other than H2O. So H2O is a base and HC2O4 is another base. So this is what they are looking for 7.1.2. Okay, 7.1.3, they are asking, is oxalic acid H2C2O4 a strong or a weak acid? Is this acid H2C2O4 a strong or a weak acid? Okay, so this is the weak acid. HC2O4 is a weak acid. That is the answer for 7.1.3. So we said it is a weak acid. Now 7.1.4, explain your answer to question 7.1.3 by referring to the data in the table. Okay, so we said it's a weak acid because we know a weak acid does not ionize completely in water. So that's the reason it's a weak acid, because it did not ionize completely. Okay, now let's look at this stoichiometric calculation question, 7.2. Now they said in 7.2, a concentrated sodium hydroxide solution, NaOH, is diluted with water to 1/10 of its original concentration. They said exactly 35 cm cubed of this dilute solution, sodium hydroxide solution, is mixed with 25 cm cubed of a hydrochloric acid solution, HCl, of concentration 0.1 mole per dm cubed in a flask. A neutralization reaction occurs in the flask according to the balanced equation. So here is the balanced equation. 7.2.1, calculate the initial number of moles of HCl in the flask for 3 marks. Okay, before we go and attend to this question, we need to understand what they are saying here. I think the proper method or the proper approach is to write or draw yourself a picture of what is going on here. So I'll do that now on a piece of paper. Okay, let me read the statement again, then I'll draw you the picture. So they said a concentrated sodium hydroxide solution, NaOH, is diluted with water to 1/10 of its original concentration. So here is a picture. You have a sodium hydroxide in a volumetric flask. You add water to it. Now, this sodium hydroxide was concentrated. I indicated that this is the concentrated sodium hydroxide solution. Then you add water to it. Now it becomes diluted. This is diluted now. So they said now this diluted sodium hydroxide solution is equal to 1/10 of its original concentration. In other words, the concentration of the diluted is 1/10 that of the concentrated sodium hydroxide. And then if you look at this diagram, I try to divide this into three parts. So in the first part, I call it the initial part. It's whereby water was added to the concentrated sodium hydroxide to become this diluted sodium hydroxide. Now what they did next now, they said exactly 35 cm³ of the dilute solution of a sodium hydroxide solution is mixed with 25 cm³ of hydrochloric acid solution, HCl, of concentration 0.1 mole per dm³ in a flask. So in the second section, they took now 35, this is the dilute sodium hydroxide solution, which was this one. So they took now 35 cm³ of it. They mixed it with HCl. HCl has a volume of 25 cm³ and the concentration of 0.1 mole per dm³. So they mixed these two. There's a reaction taking place now. And then finally, you're going to have now a final solution. You're going to have a mixture of both now. Inside, you're going to have the sodium hydroxide and you're going to have the hydrochloric acid. Now, the volume of this final mixture is 60 cm³ because the volume of the acid and the volume of the base are added. 35 cm³ plus 25 cm³ will give you 60 cm³. So I want you to have a picture now of this reaction separated into three parts. Now let's check now what they want us to do. So they said a neutralization reaction occurs in the flask according to the balanced equation HCl plus NaOH producing this NaCl plus H2O. Then the question here, they are saying now in 7.2.1, calculate the initial number of moles of HCl in the flask. So now they require us to calculate the initial number of moles of this one. So let's look again at our picture. So now we have the sodium hydroxide plus the hydrochloric acid to produce this mixture of sodium chloride and water. So this is the final mixture. But at the reacted part, they said we need to calculate now the initial number of moles of this one. So we want the initial number of moles of HCl, which is C multiplied by V. So we're going to first calculate the initial number of moles of HCl. Okay, first we need to convert now this volume from 25 cm³ to dm³. So you just say 25 cm³ divided by 1000, and then that is in dm³, you multiply it by the concentration. So let's look at this one. So we say here we have the number of moles of the hydrochloric acid is C times V, 0.1. Then 25 divided by 1000 is 0.025. Then you multiply the 2. So we have 0.1 multiplied by 0.025. Then the answer is 2.5 times 10 to the power negative 3. So this is 2.5 times 10 to the power negative 3 mole. So we do now have the number of moles of the hydrochloric acid. So let us put the number of moles here. Okay, that's the number of moles for the hydrochloric acid is 2.5 times 10 to the power negative 3. So this is the initial number of moles of the hydrochloric acid. Now if you look at the ratio between the acid and the base, you can see the ratio is 1:1, which means that the number of moles of this base is also 2.5 times 10 to the power negative 3. But let's check first what do they want us to do. The pH of the final solution is 12. Calculate the concentration of the 7.2.2, the hydroxide ions in the final solution. So they said now the pH of the final solution is 12. Where is the final solution? Remember, this is the final solution. So the pH here at the final solution they gave us, they said it is 12 in the final mixture. Now they said we need to calculate now the concentration of the OH minus ions in this final solution. The concentration of OH minus in this final solution. So let's do that one. Okay, we use the formula. pH is equals to negative log times the concentration of the hydronium ions. Remember, in that final solution you have both the base and the acid. So you have the OH ions, OH minus ions. You also have the hydronium ions because there's both the acid and the base. So they said the pH is 12, so we're going to put 12 here equals to negative log times the concentration of the hydronium ions. Then we said the concentration of the hydronium ions will be equals to 10 to the power negative 12. If you divide by log both sides, then this will be equals to, let's check now, this is 10 to the power negative 12. The answer for that one is 1.1 times 10 to the power negative 12. The concentration is 1 times 10 to the power negative 12. Now this is the concentration of the hydronium ions. So we need now to find the concentration of the hydroxide ions. So we use the following formula. So we use this formula. The concentration of the hydronium ions times the concentration of the hydroxide ion is equal to 1 times 10 to the power negative 14. Then we divide this 1 times 10 to the power negative 14 by 1 times 10 to the power negative 12. Was the concentration of the hydronium, we calculated it to be 1 times 10 to the power negative 12. So this will give us, this is 1 times 10 power negative 14 divided by 1 times 10 to the power negative 12. Then the answer would be 0.01. So the concentration now of this is 0.01. This is the concentration of these hydroxide ions. So it's 0.01. That is the concentration here is 0.01. Okay. Now let's look at the following question. I think it's the last question now. 7.2.3. Now calculate the concentration of the sodium hydroxide. Calculate the concentration of the concentrated sodium hydroxide solution. Okay, so now we want the concentration of the concentrated sodium hydroxide. Now, where is the concentrated sodium hydroxide? Remember, this one is the concentrated sodium hydroxide. All along we've been dealing with the dilute, so now we want the concentration of this one. Remember the relationship between the concentrated sodium hydroxide and the dilute sodium hydroxide. We said the dilute sodium hydroxide concentration is 1/10 that of the concentrated sodium hydroxide. So which means that if we want now this concentrated, if we want the concentrated sodium hydroxide, the concentration of the concentrated, if you want the concentration of the concentrated, it will be equals now to 10 times the concentration of the dilute. So because they told us that the dilute is 1/10 that of the concentrated, so that means that the concentrated is 10 times that of the dilute. So what we need to find now, if we can just find the concentration of the dilute, you just multiply it by 10, then we will know the concentration of the concentrated. So how we are going to do that? Okay, let's look at this again. So we need to find now the concentration of this one, the concentration of the dilute. Now to find the concentration of the dilute, to find this concentration, we need to know the number of moles and the volume. Now the number of moles initial, remember this is initial, the number of moles initial is equals to the number of moles of that which is reacted for the dilute plus the number of moles of the final solution. So we're gonna look now at the number of moles of the final solution for the base, and then we add to the number of moles of the reacted to get the number of moles initial. Then this number of moles initial, we divide it by the volume, which was 35 cm cubed, because this was 35 cm cubed, because they said 35 cm cubed of this is the one that was used to be titrated with this hydrochloric acid. So we need to find this initial number of moles first before we are able to find this concentration of the dilute. So I'm saying to find the number of moles initial, we must know the number of moles of this which is reacted, and we add it to the number of moles here, which is the final solution. Okay, if we look at this one, the number of moles in the final solution for the base is C times V. We already know the concentration of the OH ions, OH minus ions, and we know the volume, which is 60. So we're going to multiply now this concentration and that volume, then we'll find the number of moles in the final solution. So we said here what we are going to do. So we take that concentration in the final solution, we multiply it by the volume. Remember, the volume was 60 cm cubed, which is 60 cm cubed, or you can also divide this by 1000, doesn't matter. So the number of moles in the final solution is this 0.01 multiplied by this 60 times 10 to the power negative 3. So the number of moles in the final solution is 6 times 10 to the power negative 4. So it's 6 times 10 to the power negative 4 moles. Okay, so this is the number of moles in the final solution. This is the number of moles of this one. In other words, now we do have the number of moles here. It said it's 6 times 10 to the power negative 4. Yeah, so this is the number of moles in the final solution. This number of moles in the final solution. So to find the number of moles now in the reacted solution, or the solution that reacted with this acid, since we said the number of moles of this acid, since we said the ratio between the acid and the base is 1:1, so the number of moles of this HCl is equal to the number of moles of this base. So the number of moles of the base is also 2.5 times 10 to the power negative 3. Yeah, so this is the number of moles is 2.5 times 10 to the power negative 3, because the ratio is 1:1. So to find that number of moles now in the initial volumetric flask, so we add now these two So we said the number of moles initial for the base, which is in the dilute solution, is the number of moles reacted plus the number of moles in the final. So this is 2.5 times 10 to the power negative 3 plus that one, which was 6 times 10 negative 4. So we add the 2. So when you add the 2, you get the answer to be 3.1 times 10 to the power negative 3. So it's 3.1 times 10 to the power negative 3 mole. Now this is the number of moles initial. So which means it's the number of moles here. It's the initial number of moles. So we do have now the number of moles initial for the dilute solution. So let us now find the concentration of this dilute solution. So the concentration of the dilute solution, this concentration will be that 3.1 times 10 to the power negative 3. We divided, remember the volume was 35 cm cubed. So we divide now these two. Okay, so the concentration in the dilute solution is 0.0885714, etc. So we say it's 0.0885. Let's check again. 0.088571. So this is now is the concentration of the dilute solution. So if we know the concentration of the dilute solution, if we know the concentration of this one, the concentration therefore of the concentrated is 10 times the concentration of the dilute. So to find the concentration of the concentrated, we just multiply it by 10 that concentration of the dilute. So this answer here, the concentration now of the concentrated is 10 times 0.0888571. So we just multiply this by 10. Then the concentration of the concentrated is 0.885, or can say 0.886, 0.886 mole per dm cubed. So this is the final answer now for the concentration of the concentrated. So I hope this makes sense. So that's how we were able to find the concentration of the concentrated. This one, it was 10 times the concentration of this one. Okay, so this is the first video on our acids and bases. I think that was the end of it. It was 19 marks. So now I'll try to find another question on these acids and bases. So we look at another question, especially those questions where you have to compare a dilute solution and a concentrated solution. So I'll see you now in part 2 of the video.